Hello, everyone. So for anyone who wasn't present for week one or who has questions about week one, this is a video covering intro to chemistry for week one. So week one covers just like some of the basics that we're going to cover and everything like that. It's not going to take too long. And if you understood like the previous weeks, you will be okay with week one. So week one, to begin, we're going to learn about the scientific method. So the scientific method is a method of experimentation used to observe information to gain more knowledge and answer problems. It's usually a 7-step process consisting of first making an observation, so realizing that something is there. So the example that we gave in class was going to be grass growing. So we realize that grass is growing, okay? And then second, we ask a question about like something like, why is grass growing? So we conduct background research. We realize that grass grows because of water and sunlight. So because of this, and then we know that grass, from what we can tell, like from what our background research tells us, grows from water supposedly and sunlight. But to prove that, but we don't really know if it's true. So we're going to form a hypothesis. We're going to say grass grows due to water and sunlight. And to prove or disprove this hypothesis, you're going to test it with an experiment. So we have our control group and we have our treatment group. So control group is something that basically has nothing done to it, and then control group is something that has something done to it. So control group, we have grass. Treatment group, we have grass. And the control group, we're not going to give the grass water or sunlight. But in the treatment group, we're going to give it plenty of water and sunlight. And we're going to see which causes grass to grow. Our data shows that the control group, all the grass died. And our control group, the grass grew, right? From this, we analyze that data that we just got, which is all the grass died in the control group, all the grass grew in the treatment group, and we draw a conclusion. So which conclusion can we draw? We can say that the grass grows because of water and sunlight. And that it shows basically the scientific method. So an observation, a question, you conduct background research, form a hypothesis, you experiment, analyze that experimental data, and then you draw a conclusion from it. It does not have to be when it comes to science, it is okay for you to be proven wrong or something like that. You're not making a hypothesis in order to prove it right. You're just making a hypothesis to see what the data shows. If the data proves it wrong, it's okay. If the data proves it right, it is okay as well. The next thing that we're going to learn about is going to be the units of measurements. So in chemistry, units of measurements are used to know the size and magnitude of our information, and a standard comparison for the measurements, the units. So magnitude is just how big or small something is. So our basic units of measurements that we want to know is going to be kilo. Actually, no. That's going to be something else. But our basic units of measurements that we want to know is going to be for mass, like when we're measuring how much something weighs or something like that, without gravity, which is mass. We're going to use kilograms. When we're measuring how tall something is, it's going to be, the unit of measurement that we're going to use is meters. I'm 17 meters tall. Temperature is going to be Kelvin. So usually in the real world, we use Celsius and Fahrenheit for most of our lives, but in chemistry, we use Kelvin because Kelvin has a absolute zero. So when they say that Kelvin is 0 degrees, it means that it is 0 degrees. It cannot go beyond that, below that. And then amount, we're going to use mole. The reason why we use mole is because mole is going to be like something that we can use to measure super tiny small things such as atoms. And then we also have time, which is going to be seconds and measured in seconds, also minutes, but we're just talking about the basic units of measurements. And we also have volume, which is going to be measured in liters. So we're going to learn about scientific notation. So these are all the units of measurements that you want to like basically memorize. And we're going to talk about this in basically our last chapter. Our last slide, sorry. So scientific notation. So we use scientific notation to easily express very large or very small numbers and to easily show the number of significant figures that that something has. So for example, if we, let me get a sticker real quick. If we have something, a big, huge number, like, one second. We have a big, huge number, like 32,000. But we want to write it in scientific notation, which is like a simpler form. What we're going to do is we're going to realize that, so first you want to know every single number, no matter how small or how big that number is, it always ends up with a decimal, but we just usually don't write a decimal because it's like not needed. It takes a lot of time. So we're going to start with a decimal and we're going to move 4 places to the right. 1, 2, 3, 4, until only one number is in front. And since we moved 4 places to the, basically to the right, is going to be 3.2. And because it's going to be 3.2 times 10, 32,000 to the 4th power. And honestly, this figure over here, when it says places to the right, that can be confusing. Just ignore this. We're actually moving 4 places to the left. And since we move 4 places to the left, that's going to be a positive 4. So 3.2 times 10 to the 4th, which if we calculate this will equal 32,000. And then if we have an extremely small number, like 0.00032, that like takes a lot of effort to say and everything like that. So in order to write the scientific notation of this, we're going to move it we're going to move it a certain amount of places to the right. So we start over here with the decimal, and we're going to move 1, 2, 3, 4. And we're moving backwards, right? So because we're moving backwards, it's going to be a negative number. And then also it's going to be 10. We're always multiplying by 10. We know that this is going to be, it only has the 3 in front of it. Just ignore the zeros. It only has a 3 in front of it, so it's going to be 3. And then after the decimal, it's going to have 2. So 3.2 times 10 to the what? So we moved 4 places backwards. So it's going to be 3.2 times 10 to the negative 4th power. And that's how to do scientific notation, where n is a number always from 1 to 10. X is going to be positive or negative depending on if we're making the number smaller or we're making the number bigger. All right, so the next thing that we're going to discuss is going to be rules for conversion when it comes to scientific notation. So when it comes to large numbers, exponent is always going to be positive. You move the decimal to the left until n is between 1 and 10. The number of places is going to be positive exponent. So let's just say a big number like 72 million, right? And we want to make it a little bit smaller. We always know that in each number, we always have a decimal after it, no matter how big or small. Like 7, we can just write 7 point. with like imaginary zeros. It's always there. We just never write it like that because it's just too much. So if we want to draw this and write this in scientific notation, like we said, we want only one number to be in front of the decimal. So we're going to just move this and we're going to move it to the left. So since we're moving it to the left, we know that it's going to be a positive exponent. So it's going to go 1, 2, 3, 4, 5, 6, 7. So we ended right over here. We have 7.2 times 10, always times 10. And we moved the decimal place 7 times 10 to 7. And we're not going to say -7 just because we move it to the right and we didn't move it backwards. And this basically represents a larger number. So this is going to be the scientific notation. If we look at over here, for small numbers, we have this extremely tiny number. So we have 0.00005. So we start where the decimal place is at. If it's not there, you know where the imaginary decimal is, and you're going to move it a certain amount of places to the right. You're moving it to the right, that means the exponent is going to be negative. So, and it's also going to be negative because we're representing a smaller number than initial. So it's going to be 1, 2, 3, 4, 5, 6. Only one number that's not a 0 in front. So it's going to be 5.00. You can do that, or you can just write 5 times 10, always multiply by 10, to the 6. And because we're moving backwards and we're representing an extremely small number, it's going to be negative. So that's going to be how to do the scientific notation. If you want, you are more than welcome to do these practices. It should help you with scientific notation and everything like that. If you are able to do them like by yourself, you're good with this chapter. If not, please be sure to come to office hours and we can practice and we can do these for the homework together. The next topic that we're going to discuss is going to be significant figures. So for my opinion, this is going to be the hardest, one of the hardest topics that we're going to cover for week 1. So significant, but it's like once you get it, you get it. So significant figures, also called sig figs, are digits in a number that express how precise a measurement is. They include all digits that are known with certainty plus one estimated digit. So what this basically says is if we're measuring something like how tall is this? Like this thing right over here, how tall is it? So we have a ruler, right? And this rule is like 1 feet, 2, 3, 4, 5, 6. So despite us knowing that it's at least 6 centimeters, we don't know if it's exactly 6 centimeters. Like, is it 6.1, 6.2, 6.3? Because of that degree of uncertainty, we're going to write 6, which we know for certain, and we're going to write basically that degree of uncertainty. And that's basically sig figs, what sig figs are going to represent. So there are going to be 4 rules for significant figures. The first rule is going to be any number that's not a 0 is going to be significant. So we have a number like 345. Because all these numbers are not 0, they're going to be significant. And then the next thing is going to be if you have basically these if you have non-zero digits that are surrounding like, and you have zeros in the middle, the zeros are going to be significant as well. So like 1 surrounded by 0, 0, 3. These two zeros surrounded by 1 and 3 are going to be significant because they're in the middle of non-zero digits. The next thing is going to be leading zeros. So leading zeros are going to be anything. So they don't have, as you can see, they don't have a non-zero digit in front of them or anything like that. And they're just a bunch of zeros and then 2, 5. The only ones that are significant is going to be the non-zero numbers. And then any leading zeros before non-zero digits are not significant. And then lastly, trailing zeros at the end are significant only if there's a decimal. So if you have something like 1500, because there's no decimal over here, it's not going to be, these two zeros are not going to be significant, and it's only going to be two sig figs. But if you do have a decimal, it's going to be significant. Like all of them are going to be significant, including the two zeros. And similar rules apply to multiplication and division. So multiplication and division, round your final answer to the same number of significant figures as the measurements with the fewest significant figures. So basically what this means is if we have a number like 3.24 and 7.1, so we know that this one has three significant figures, and we know that 7.1 is going to be two significant figures from our rules. From our rules. So if we're looking at this and this, we want our final answer to represent the measurement with the fewest sig figs, which is going to be 7.1. So our final answer should only have two significant figures. So despite our answer becoming like this big number, 23.004, we're only going to say 23 because we want our final answer to be rounded to the measurement with the fewest sig figs, which was 7.1. So it's going to be 23 as our final answer. And then for addition, it's going to be a similar rule, but it's going to be looking at decimal places instead of just like the number of significant figures. So we look at this number and we see that the one that has the fewest sig figs is going to be 18.0. The one that has the fewest number of decimal places is going to be 18.0 with only one decimal place. This one has two decimal places. This one has three decimal places. So our final answer should only have one decimal place as well, because that is going to be the fewest number of decimal places when it comes to our numbers that are calculated. So the final answer is going to be 31.1, matching 18.0 with one decimal place. So we're going to practice sig figs real quick. So if we look at this one, you can go ahead and pause the video and just like try to do this by yourself and see if you get the correct answers. Just to practice. If not, it's okay. We can do it together. So we have this one. But I highly recommend pausing the video if you like haven't covered week one, just to make sure that you know it by yourself. So we have something like 0.007080. So we automatically see these numbers 0, 0, 0, 0. And we see that these are leading zeros and they're not going to be significant. And then we know that any number that's not a zero is automatically going to be significant, right? So we're going to keep 7 and 8. They're going to be significant. So we know we have at least two significant numbers. And then we look at 0, 8, 0. So we look at 0 over here, which is going to be in the middle of sig figs. So it's going to be of two non-zero numbers. So it's going to be non-significant. It's going to be significant. And then we also look at this 0. So this 0, because it doesn't have a decimal in front of it, we know that it's not going to be significant. So our final answers for how many sig figs is going to be 3 in total. And then we're just going to verify this. With our rules. And then our next one is going to be calculating and rounding for multiplication. So multiplication, we discussed that is going to be following the number of significant figures. So if we multiply 2.4 times 3.15, calculator, 2.4 times 3.15. So we get answer 7.56. But since our least number of significant figures is going to be 2, we're going to just round it. So it's going to be 7.6 for our final answer. And then for adding, it's going to be 4.56 plus 1.4 plus 12.003. So we have 4.56 plus 1.4 plus 12.003. And we get 17.963. And then we're looking at the fewest number of decimal places. And our final answer is going to be 17.963. But since we're looking at fewest number of decimal places, it's going to be 17, we can just say 18.0. All right, so now we're going to cover So now we're going to cover dimensional analysis, which is basically going to show like ways to convert units. So like we covered at the beginning, length is going to be equal to meters, mass is going to be equal to kilograms, time is going to be equal to seconds, temperature kelvins, and then the rest, electric current, ampere, amount of substance is going to be mole, luminescence intensity is going to be candela, CD, represented by CD. So all of these are going to be the common units that you really want to memorize, but honestly in this class you don't really have to memorize electric current or luminescent intensity because you don't really deal with it a lot when it comes to chemistry. Ampere, you're going to deal with it like later on when you're dealing with something like pressure. But you also want to know your common prefixes. So your prefixes are going to be like basically like femto, pico, nano, micro, all these numbers that basically like prefixes that basically go in front of your common units to basically represent them, to simplify their numbers. So something like kilogram is going to be kilo. Kilo stands for 10 to the third power. So if we're saying something is going to be 1 kilogram, we're basically saying that it's 10 to the third power gram, which is going to be 1,000 grams. And you're going to do it for every single one of it. So it's going to be like milli. Something is milli, a millimeter is going to be 10 to the negative 3 meter, which is going to be 1,000 meters. Wait, not 1,000 meters. It's going to be 0.0001 meters. So that's what basically 10 to a millimeter is going to represent. All right, so dimensional analysis. So the steps for dimensional analysis is you basically start by identifying your start unit, and then you identify your end unit. And then from there, you're going to use like a fraction to cancel the units, and then you're going to check your answer. So it's very simple. You guys are going to do great in this. We're going to do some practice. So we're going to do the hardest one. And if you can do this one, you can do all of them. So we're going to do number 2. So we're first going to start with our first step. We're going to identify the start and we're going to identify the end unit. So the start unit, if we're looking at convert 1,500 millimeters per second, so we're dealing with multiple per second, to meters per hour. That's what it tells us. So we know that we start with millimeters per second and we end with meters per hour. We want to end the unit as meters per hour. So I have this over here, but I'm going to go ahead and basically show you how we're going to do this. So we have 1,352 millimeters per second. So starting over here, you're going to multiply this. And the first one that we're going to try to get rid of basically is going to be the millimeter. So we're going to do, 1 meter equals how many millimeters? 1,000. And the most confusing part that I see people like being confused about is like which one goes to the top and which one goes to the bottom. So if you're ever confused about this, remember that the unit that you want to end up with is going to go to the top, and the unit that you start off with, the one that you want to get rid of, is always going to be at the bottom on the denominator. So we're trying to get rid of millimeters to end up with meters. So we're going to do meters at the top, and we're going to do millimeters at the bottom, and 1 meter is equal to 1,000 millimeters. So then if we do this, we're going to get rid of millimeters and we're going to end up with meters, and that's going to give us our first part, meters, but we still don't have hours. But so we're going to try to make seconds into hours, right? So in order to do seconds into hours, you're going to first start off by, so the one that we want to, following this rule, the unit that we want to end up with is going to be minutes. And the one that we want to get rid of is going to be seconds. So we know that 1 minute is going to be 60 seconds. And then from there, you're going to do, you're going to basically want to get rid of your minutes. So it's going to be at the bottom, and you're going to end up with your hour. So we know that 1 hour is equal to 60 minutes. And if you basically calculate this entire thing, that's going to give us our answer. So let's go ahead and just calculate it. So we have 1,352 millimeters per second to meters hour. And you end up with 4867.2 meters per hour. And that shows dimensional analysis. And if I'm looking over here, I'm just gonna go ahead and reverse this real quick because this is wrong. Because despite us wanting to get, this is actually in reverse. I'm sorry, y'all. So this is going to be 60 minutes and it's going to be 1 hour. So the reason why that one was wrong, like in reverse, is because so I forgot that the seconds is going to be at the bottom. So it's going to be actually in reverse, where you basically have the unit that you want to end up with at the bottom, and then the unit that you start with at the top. So just keep that in mind, because mistakes like that can happen, and then when you have that, it can give you like the wrong answers. So that covers dimensional analysis. If you guys have any questions, just let me know. I'm sorry about that mistake over here for this one. And I'm just going to go ahead and delete this part. Okay. All right. You guys have a good day. Thank you.